So these lectures are going to be on elasticity, ending up with hopefully a fairly thorough treatment of the sort of stuff that I talked about on yesterday on topological lattices. So I'm going to start off and look at classical Lagrangian elasticity. This is something that you sometimes see in your freshman or sophomore course, but most of the time physicists don't do a very good job on elasticity. They make it too simple, actually. And then I'm going to look at, phonons and excitations of the elastic media. And then we'll talk about lattice models, which are basically ball and spring models whose continuum limit give you elasticity. Then finally, we'll move on to the Maxwell lattices, which we discussed a little bit, and spend a fair amount of time getting that straight, looking at the excitations of the Kagame lattice. And then I'm going to do I hope, about an hour on something which we call mechanical graphene. This is a model whose phonon excitation spectrum replicates exactly the electron excitation spectrum of a strained honeycomb lattice. And then we'll get to the topological phonons. Now, I'm not sure I'll be able to get through it all. It's been a while since I've lectured like this at the blackboard, and my speed may be too slow, so I may have to cut out some things, but that's okay. So let's start with classical elasticity. So this is an old topic. It goes way back to probably the 18th century, but most of the progress was done in the 19th century by people like Lagrange and Euler. Euler's probably a little earlier. But basically the idea is that, you look at any material and you don't see any microscopic structure in it, right? It's something that looks like a continuous distribution of mass. So you think of matter as being some continuous distribution of mass. Maybe it's shaped like this, who knows? And there are points on this manifold, if you want to call it that, which we'll label by point X. So imagine that there's an equilibrium for this, an unstretched equilibrium for the material. So if just put it down on the table, it will not change its shape. And then you do something to it, and you go to another shape where the point X gets mapped to a point R of X. So this presumably has deformed the material in such a way that it is, there's energy stored in the springs that have been stretched. But if the transformation just involved a rotation, then there's no energy cost to go from the original to this one. Now, we don't know anything at this stage about the microscopic structure. The theory of elasticity was developed before people really knew what atoms were. But they had a sense that, if you went from here to here and you stretched, there could be slow variations on some scale, and you would want to describe the transformation from here to here in terms of saying that the ith component of this vector just involved a uniform distortion or transformation of X. So I'm going to use this notation for reasons that will be clear in a minute, that I is going to refer to the final state. That's the index that goes with this guy, and the Greek letters go with the original. Now, in essence, we can think of the original state as being a space, and it gets mapped into another space, which isn't the same. They happen to coincide before the stretch, but they really are distinct. I can do operations on this without affecting this, and the other way around. So we'll write things like this. Excuse me? Do I want to call this homotopy? I mean, yeah, there are all kinds of fancy names you can use for it, but basically I don't think it has all the restrictions that go with homotopy. It's stretching and compressing and so forth. It's just going to describe the change in shape. I'm not going to do any fancy homotopy theory for this. So this guy's called the deformation tensor. And in the engineering literature, you will find that that guy plays the principal role. It is not what we call the strain tensor. We'll get to the strain tensor in a minute. At least it's not what physicists call the strain tensor, though it's sometimes called that. But it's really, we'll call it a deformation tensor. So now, if this guy can be a delta function, in which case R is equal to the original, and we will write lambda I alpha equal to delta I alpha plus, I'll use the term normally, eta I alpha, where eta is small. When eta is 0, there's no stretching or no rotation even, and you're left with the delta I alpha. So we will also, in that spirit, write the vector R of x as being equal to the original position, x, plus the displacement u of x, so that, if I look at this derivative, well, I guess I should write it out explicitly, that lambda I alpha is by this definition equal to dri dx alpha, which would imply that this is equal to delta I alpha plus di dx alpha. So this is the thing which we're calling eta I alpha. Okay. So U is usually called the displacement variable. It's telling us, how much things have changed. So, lambda encodes lots of information about what the shape changes are. Lambda can have various forms. There's the isotropic form. So let's imagine that we're in a three-dimensional. I should have said something here. Now, this guy we're going to say has spatial dimension D, and this guy spatial dimension capital D. Now, they don't have to be the same, but these lectures will mostly focus on D equals capital D. But for example, suppose I had a sheet of graphene. There, it lives in the graphene is a two-dimensional sheet, but when it gets distorted, it lives in a three-dimensional space. And the sort of things we'll be talking about here can actually be generalized. And some of the nonlinear properties that come out of this kind of a transformation are really quite important because low-dimensional systems have lots of fluctuations, and the nonlinear terms become very important. But for the moment, we're going to assume that this is true. So let's just look at D equals 3, and we'll look at an isotropic lambda. So I'll generally use the notation that if I have a tilde under it, that's the tensor itself without its indices. So here we write lambda 0, 0, 0, lambda 0, 0, 0, lambda. And that tells us that we stretched the material or compressed. If lambda is greater than 1, we've stretched the material in the three directions equally. And in the process, we will change the volume. So if I look at the ratio of the volume after the stretch to the volume before, this just is equal to the determinant of this matrix lambda. And since it's, it's a square matrix right now, that's well defined. That tells us that if we look at a smaller volume element, D3x, we want to relate that to D3R, and that would mean that I'd have to put a determinant lambda down here to make the transformation between the two. Okay, so that's one type of thing. Now, anything that doesn't change the volume is a type of shear transformation. So we have shears are distortions in which the determinant of lambda is equal to 1. Okay? So they go under various headings. There's something called, there are various ways you can do shears. Since the lambda itself in 3 dimensions has, the strains there are 6 degrees of freedom, which we'll get to in a minute. One of the degrees of freedom is the change in the volume, and then there are 5 left over that are shears in 3 dimensions. In 2 dimensions, there are 2 shears and 1 compression. So some pure shear corresponds to the following. You have lambda to the minus a half, 0, 0, 0, lambda to the minus a half, 0, 0, 0, and lambda. So you can see that the determinant of this thing is indeed equal to 1. And what we've done is we've taken a block like this, and we stretch it so that this gets a little bit smaller, and it's stretched out in the z direction. You pull it out in the z direction, and you compress in the x and y direction in such a way that you preserve the total volume. Another thing you can have is what's called a simple shear. And that has a lambda that looks like this. Obviously, oops, there'd be a 1 here. There's a 0 here. Obviously, the determinant of that is 1. And what you've done is to take a rectangle, say like this, and you have, in this case, this is the, the distortion is this guy. So let's take this to be the x direction. And as I go upward, the z is proportional to x, and the tangent of this angle is equal to gamma. Okay? Now, of course, as I said, we can do operations on the target space. I guess I didn't reference this, so just to remind you, we're going to call this the reference space. And this the target space. So, for example, if I have this kind of a distortion, I can post-rotate it. And, for example, take this guy so it's over to here. And then I have distortion that looks like that. There, the distortion's still the same. I've just rotated it so it goes around to a little bit of an angle here. Or I could have done it so it's halfway between. Well, I'm not very good at drawing that. So that you have equal angles here. So if you take a rectangle, and the simple shear would be I'm pulling like this, but I could also have put it like this and pulled on it, and you would call it a simple shear because it reproduces this kind of a configuration. So the two are mixed up, and it depends a little bit on what the symmetry of the original lattice is. So now this isn't, as I say, the engineering literature uses these variables as the fundamental ones quite often. But there's a disadvantage to them in that you have to keep track of whether or not you've rotated the sample. The stretching doesn't involve any of the post-rotation, so it's useful to have a definition of the deformations that take place, or measure the definitions that hide the fact, that just make the rotations go away, so you don't see them at all. And the way that's done is to introduce a metric tensor. So if we go back to our reference state, suppose we have 2 points x and another point over here, x plus dx, where this is the distance between the 2 points dx. So the x plus dx gets mapped into a point r of x plus dx, right? And so then we imagine we have springs here that says that the distance between these 2 points doesn't want to change. So if I have a spring like this and I stretch it and then rotate it, that hasn't, I have just the stretch that takes place, and we would like then to have a measure of what that stretch is instead of exactly where everything is. So what we do is to say, what happens, how big is dr squared, it's the length squared, as compared to basically dx squared. In other words, how much have things changed? And this should be familiar to you as involving something that's like a metric tensor. I guess I can move over to here. I can write dr squared is by definition dri. I'm using, or will use, the Einstein convention quite often, so I'm summing over the i's. Well, this is equal to lambda I alpha dx alpha lambda I beta dx beta, or I can write that as lambda transpose lambda alpha beta dx alpha dx beta, right? And this you should recognize as being the metric tensor G. It tells you the difference between the separation in the original reference lattice and the final lattice. Right? Now, notice that if I write this out, this is lambda transpose, this G alpha beta is lambda transpose alpha I, lambda I alpha, or I can write this as DRI. I'm sorry, this should be a beta. DRI dx alpha, DRI dx beta. So we're summing over this internal index, which says that if I come in and uniformly rotate the whole lattice, both of these rotate the same amount, and that doesn't change. So what I have here is the metric tensor is a tensor in the reference space, not in the target space. And so what we'd like to do is to have a measure of how much things have changed, and I'm going to write this as I want to write this as I want to look at dr squared minus dx squared. So this is going to be G alpha beta minus delta alpha beta times dx alpha dx beta. And this thing we're going to call twice U alpha beta. So this U alpha beta is what we call the strain. Certainly in all of the physics literature, it's this guy that's the strain. And notice that this is not a linear function of the small displacement U. It's a nonlinear function because this is going to be equal to, recall that G alpha beta is, so this is lambda transpose lambda alpha beta minus delta alpha beta, and yeah, so that's what it is, which is, recall that lambda, I guess I need to keep myself bigger, so lambda is equal to, there's an I alpha, delta I alpha plus d alpha on ui. So I'll use this notation that this means the partial derivative with respect to x alpha, and we have a ui there. So we can write out what, write a bigger here, what lambda alpha I transpose lambda I alpha is, this lambda I beta, this is delta alpha I plus the alpha ui times delta alpha, delta beta I plus d beta ui. So this is then equal to delta alpha beta plus, now this sets, so I multiply this guy times this guy, it sets I equal to alpha, so I get a d alpha u beta plus a d beta u alpha plus a d alpha ui d beta ui. So you can see that when I subtract off the delta alpha beta here, I get this thing with a factor of a half, which is what we're calling U alpha beta. So what we usually do, which you see in almost all physics textbooks, is the strain is the symmetrized deformation tensor here. without this term. This guy is critical to preserve rotational invariance. So if you don't have that term, and you take your thing and you post-rotate by theta, then the linearized theory is valid to second order in theta, to theta squared. But if you rotate it more, it is no longer correct. So you can now do things like, we can go back and express what is delta V over V0, which was the determinant of lambda. But the determinant of lambda is equal to the determinant of lambda transpose. So I can write this as determinant of lambda transpose lambda to the 1/2 power, which then allows me to write this as determinant of delta alpha beta plus 2u alpha beta, all to the 1/2 power. And then I can expand this out. What is the determinant? The determinant is the exponential of the trace of the log of delta plus 2u. And this guy I can write then as trace of, and there's a one, it's to the 1/2. So there's a 1/2 that comes out here. So this then becomes trace u in the small u limit. And if I write that out, this then becomes, I don't want to do this now. I'm taking the determinant. So the delta, if I expand this, I don't have a delta, then I expand the exponential, it becomes 1 plus the trace of u, and delta v over v. Well, I forgot the -1 here. Yeah, that's, I meant to make this be a -1. So there's a -1 here, a -1 here. So linear order in u, delta v over v is trace u, which is just divergence of u, if you wish. If we linearize, right, and ignore the nonlinear term. So that allows us then to take this u alpha beta, which in 3 dimensions has 6 independent components. Because it's a symmetric tensor. And we can take one of them to be trace u, which in the Einstein notation is u alpha alpha. And then the 5 that are left over are the parts that are orthogonal to that. So we can introduce a symmetric traceless tensor. 1 over d delta alpha beta u gamma gamma. So this is the symmetric traceless strain tensor, and it has 5 independent components, and they describe the various strains that I had over there. Okay. Now, there are other strains that are used in the literature. The notes will tell them. I'll just tell you what they are. There's an Eulerian strain that focuses on derivatives with respect to the actual lattice. So, I can write dx alpha is lambda inverse alpha I dri instead of the other way around. And then I can look at dx is equal to let's see, dx is a lambda inverse dr. And you can then define, since the lambda inverse is dx alpha dri, you come out with something called the Eulerian strain, which is dx alpha dri plus, this is dxi drj dxj j dri, and then minus dx alpha dri dx alpha drj. So we've mixed up the alphas and the betas here because of, in the initial state, the two are the same. But there is a nonlinear term here. Notice now, we're talking about derivatives with respect to the state after you've stretched it, which I find a little confusing at times. And we have a trace here over the original reference space variables. So this guy is invariant with respect to rigid rotations of the original lattice. Now, this is not so useful. Well, it's useful if you live in a world where your elastic medium is isotropic. Now, there are lots of systems that are approximately isotropic. You take a piece of rubber or a piece of paper like that, or you take a piece of steel that's full of grains that are sort of isotropically oriented, and you end up with something that on a large enough length scale actually is sort of isotropic. And if that's the case, then writing a theory down in terms of this, or there's another tensor they use, rather than basing the stretching on the lambda transpose lambda, which was a tensor in alpha beta, you could look at a tensor lambda transpose instead of lambda transpose lambda. This is a tensor in I and J, and it has the same property that it's invariant under rigid rotations in the thing. So these have names. I think, I forget what they're called. I'll tell you here in a minute. This guy is called the finger tensor. This should be an inverse and a transpose here. This is the finger tensor, and this is the left Cauchy-Green metric tensor, and the other one is the right Cauchy-Green one. So we're going to exclusively use the one where we have rotational invariance with respect to post-rotation. And then this also allows us the possibility of saying, well, when I write down my energies, which we'll do in a minute, something has to reflect the symmetry of the original lattice. And the symmetry of the original lattice usually is some point group symmetry associated with, well, I said it the wrong way. The original target space, for modern world, recognizes the fact that there are anisotropies. Your solids are based upon, simple lattices. And that means that when we get down to writing what the energies are, we have to keep straight what the symmetry operations of the original lattice are, which really is associated with the crystalline symmetry that it has. Okay. So that brings us to the energy. And I see that, I'm not sure. So that using this water thing, which I wash my windows with, is the recommended behavior here. I don't know. Oops. Oh, golly, it's all wet. Jesus, I think this is not working. Let me shake it out a little bit. No, it's still not working, boy. Huh? You just have to do it that way. Okay, thank you. That's what I need. Okay, so our next step is to write down the energy. Now, as long as we're talking about the elastic limit, which is, remember, think of it as being a long length scale compared to microscopic distances in the sample. So if we're talking about a standard piece of aluminum, the microscopic length is in angstroms. If we're talking about a colloidal solid, the microscopic length is in, the 10 micron scale maybe. And you can go to even larger if you want. Let's see, there's a dry thing that dries the board here. Okay, so we can certainly start with the idea, start out here, that you have a free energy density. So there aren't enough symbols in the world to treat everything. So you have to get used to having the same symbol being used for different things. I don't know if any of you have taken mechanical engineering courses. There's a guy named Truesdale who's written the Bible, what they call rational mechanics. It's about that thick, and the first 20 pages are explaining all of the symbols, that none of which will be repeated. He has to use the Latin alphabet, the Latin bold, Latin, what do you call it, italic, capital letters, and then uses the Greek alphabet, and then uses the Russian alphabet, and he uses the the Hebrew alphabet. And to make things really be great, he uses script German, and nobody even knows what to call them are. So, but he did it right, and the physicists didn't. Okay, so we're going to have an elastic free energy density. Now, you know, energy or free energy, they're certainly, for any real system, they're going to be entropic as well as energetic or enthalpic contributions to the energy. So usually when we talk about elasticity, we talk about the free energy, which is a natural function, not of the entropy, but of the temperature itself. So we'll just use this symbol. And it could be, you can view it as a function of the lambda alone, but if we know that we have this post-rotational invariance, we can also insist that it be a function of the u instead of the lambda. So this thing, you know, the lambda, the elastic energy, has invariance with respect to certain operations on the lambda. So I'm going to write this as u lambda times v inverse. So u are the set of operations that leave the, you know, that include the post-rotation. So that's the rotations after I'm done. Yes? You know, you can do with either. I would probably prefer to think of them as being as a function of the density, which is volume. I mean, you don't want to, the density of the original sample. But remember what we're doing, we're changing the density, we're changing the volume, so you have to be careful. Excuse me? Oh yeah, there's a, yes, there's a PDV, and I'll show you how that comes out in a minute, yeah. I'm mostly going to ignore that effect. Adding the pressure or external stresses actually complicates considerably the description of the lattice. And so I don't get off into a tangent where I have to worry about internal stresses and so forth. I probably won't talk about it, but it's present, it's there. So as we've said, we have this invariance with respect to this guy. So what we can do instead is write it as F elastic is a function of our stress tensor U alpha beta, and the energy is invariant with respect to these operations. Yeah, V is the, U is has to do with the target space, V has to do with the reference space, and you know, if I have a cubic lattice, then there's a set of point group operations, or if I have a lattice, there's a set of point group operations which leave the energy invariant. So for example, if there's a cubic lattice, then if I rotate by 90 degrees, I don't have the same thing. And that invariance with respect to that type of operation controls what the exact elastic energy is to get down. So we're at the moment just going to say it's a function of the U tilde, with the understanding that where the energy itself is going to be invariant, is going to reflect the symmetries of the original state. So, you know, of course, we haven't specified what the function is. The simplest thing to do is to include functions only up to harmonic order in U. So what we usually do is write this as 1/2 integral over the volume of the material in the reference space times a tensor K alpha beta gamma delta U alpha beta U gamma delta. And then, of course, depending upon the system you're looking at, you may want to go to higher order terms. But notice now what we have is something that's quadratic in the U's, but these are the full nonlinear U's. So this guy really is invariant with respect to macroscopic rotations of the reference state. This K alpha beta is the elastic constant tensor, or the tensor of elastic moduli, if you wish. It's a fourth rank tensor, and that's enough to, scare even strong people. But we can say a lot of things about this. So first of all, K alpha beta gamma delta multiplies the U alpha beta U gamma delta. And of course, if I were to interchange gamma delta with alpha beta, I can't change anything because this part doesn't change. So amongst the symmetries we have for K alpha beta gamma delta is equal to K gamma delta alpha beta, because I can interchange these two things. And U alpha beta, as we constructed it, is symmetric, right? I mean, you can saw how we wrote it down. It's a symmetric tensor. So that means that this is also equal to K beta alpha gamma delta was equal to K alpha beta delta gamma. So, that restricts the number of components of K by a fair amount. It means that, let's see, what is the number now? I think there are 21 independent components of K alpha beta gamma delta in 3 dimensions. So, how can we go about constructing what the elastic moduli are going to look at? Well, one thing you can do is look at what the reference space gives you in terms of variables that define directions. If we start off with an isotropic solid, and so think of a piece of rubber. Rubber is macroscopically isotropic, at least. Microscopically, it's not isotropic, and that sometimes leads to some confusions. So what that says is that in the reference space itself, the only tensor we have to deal with is delta alpha beta. So what we want to do is to construct a rotationally invariant fourth rank tensor just from the unit matrix. So what we have here is K alpha beta gamma delta. We can write as lambda delta alpha beta delta gamma delta. Notice when we have a delta alpha beta operating on the U, I get trace U. So this thing is clearly telling us something about what happens if you change the volume isotropically. But I can combine alpha with gamma instead of with beta. So we can have a delta alpha gamma delta beta delta. That is an acceptable combination of terms of the reference space, but this doesn't satisfy the symmetry operations I just gave you. And to make that happen, what we have to do is to change and make this beta gamma. And you can go through and look and convince yourself that that satisfies the symmetry operations, all of the symmetry operations that we had. So these are called the Lemay coefficients. And this is the physicists tend to like this. Certainly, it's the form I use. But there's another form that's useful also. Remember, we broke up the strains into those which preserve volume and those which don't preserve volume. This thing has terms in it that preserve the volume, even though it's a little bit hidden. So we have another way of writing this, which is B delta alpha beta plus mu delta alpha gamma delta beta delta plus delta alpha delta delta beta gamma minus 2 over D delta alpha beta delta gamma delta. And this is arranged so that if I take the trace with respect to alpha beta, so let me take this term here and do the alpha beta trace. So that means I set alpha equal to beta and I sum. So this term gives me delta gamma delta. Alpha set to beta, it gives me again delta gamma delta. then I have minus 2 over d times, I'm taking a trace with respect to alpha beta. The trace of delta is d, so I multiply this times d, and here I have a delta gamma delta. And you can see now that the sum of all of those is equal to 0. So this part here restricts us to parts that are orthogonal to the uniform change. This now measures purely, I guess I left out a delta gamma delta here. So this has all of the parts, at least to linear order, that describe the change in the volume. And this B is called the bulk modulus. As basically it's changing the bulk volume. And mu is called the shear modulus. And the 5 independent shears that we discussed earlier are measured by this energy, and they're all equivalent because it's isotropic. So all of the shears cost the same energy. Okay, so if we look at what does F elastic look like, then is equal to, so that's the energy density. This is 1/2 lambda U alpha alpha plus U alpha alpha squared, rather. How do I want to write this? Actually, I prefer to write it in terms of the B. Remember, the ST is a symmetric traceless version, and so you get it out like that. It's worthwhile doing one other example. Let's do a uniaxial crystal. So a uniaxial crystal is one in which there is a direction picked out, single direction, and everything perpendicular to it is isotropic in that plane. So now, in addition to the delta alpha beta, we have this matrix, this vector in alpha, which specifies the direction of the anisotropy, and we have a constraint that it's not a polar system, so n alpha and minus n alpha are the same thing, so we can only have quadratic combinations. So this is what you would get here. There's a K1, everything in the along the in direction. Then you have K2. Let's see, I want to do, yeah. So then we have n alpha, n beta, and we're going to mix it with something perpendicular to that. So I'm going to introduce this tensor delta t gamma delta plus n gamma n delta delta t alpha beta, and then plus, let me make sure I want to do this one right now. Yeah, K3 is delta alpha beta transpose, or T rather, delta gamma delta T, where this delta alpha beta T is the projection operator perpendicular to the n vector. So I've gotten 3 terms, but they've all been mixing only the alpha and the beta. We can now have a term, let's do this one the way I've done it here, a K4, delta alpha gamma delta beta delta plus delta alpha delta delta beta gamma transpose. Now notice that if I just look in the plane perpendicular to the n direction, I have something, a part of the energy, which is the same form as I wrote down over here, except I didn't put a factor of 2 here, and I probably should put a factor of 2. Well, I don't have, I might have put a factor of 2 here. No, let's see. No, I've got it right. No, this, if I look at this one, this is the same thing as this set, projected into the plane perpendicular to it. And then we finally have something, a K5, where we are mixing the n's with it, n alpha gamma delta beta delta, well, I'm sorry, n alpha n gamma delta beta delta transpose plus, and now this goes on, alpha, delta, and delta transpose beta gamma plus n beta n gamma delta transpose alpha delta, and then n beta n alpha delta alpha gamma. So that's, what you would get for a uniaxial system. Now we're going to be dealing with lattices which are which have very low symmetry. Which means that we really have to have a somewhat better way of organizing the elastic moduli. And what we'll use is something that is inspired by a guy named Voigt. And later there was Kelvin, I think it was. Kelvin did another variant on this. So what they did here, we just have everything written out like this, and you'd have to write out your sums to keep straight what the gammas and the deltas are, and have you written it out. What we're going to do now is to exploit the fact that the strain tensor is a symmetric tensor. So there are 6 independent components in three dimensions and 3 independent components in 2 dimensions. So we can define I'll just use this notation now to represent the set of, I'm going to write in a vector form the set of independent components of the strain tensor. So this is uxx, uyy, and uxy. So those are the 3 independent components. Depending upon which of the conventions you use, Voigt would put a 2 here, Kelvin would put a square root of 2 in this, and I put nothing there. So I'm just going to use this as the definitions. In 3 dimensions, we have uxx, uyy, uzz, uxy, uxy, ux, z, and uyz. I do it that way. I think I made a mistake in my notes. I think I wanted to do it. No, that's okay. I'm not going to do too much in 3 dimensions. The order of these things is slightly different in different places. So Voigt had a particular way of doing it as a circle. So what that means is, let's look at 2 dimensions just to make things simple. That means that there's an elastic matrix, which we can write down, which basically has the following components. Now, you might say that's the correct way of writing things down, but this does not take into account the fact that, if you have tensors like this, you have all of these permutations which give you the same thing. So what I'm going to do is to put a factor of 2 here, a factor of 2 here, 2 here, and 2 here, and a factor of 4 here. So why do I do that? This K alpha, this guy comes from one of the terms in the matrix So I have to take out of this sum all of the terms for which I have uxy here. So I can have a kx, kxy, kxy. That's one term. I can have a k yx, xy, a kyx, yx, and a kxy, yx. So each of those terms appear in this series, and the way we take that into account is by putting a factor of 4 here. Similarly, if we look at the off-diagonal one, where we have, I want to get this xxyy, so I can have kxxyy, I can have kyyyxx. Right, so there are 2 of these, and so I have 1 here and 1 here, and when I multiply it out, I get a factor of 2. The more interesting one is the kxxxy. We can have kxxyx, kxyxx, and kyxxx. So again, there are 4 of those, and that comes with a factor of 2 here and a factor of 2 here because it's not that diagonal one. So that's the notation people use. I have fouled up on many occasions and used inappropriate notation myself, so it's worth thinking about and knowing it. Okay, so I think we've done enough with the strains. The next thing we want to know about are forces and stresses. Okay, so we have this elastic body, and let's look at a little element inside there. Now, the only way it can experience force is from the forces that the medium around it exerts on there. So we have a force density. Now let's see if I can write here. So this is the force per unit volume that the medium itself exerts on this volume located at point X. Now, because of the fact that there are no internal forces or external forces that act directly on it, that only comes from the volume, this thing has to be a gradient of something. So we're going to write this as d alpha sigma I alpha. And so this is a tensor now. Notice it's a mixed tensor. It has an I here and an alpha here. But this sigma is the force per unit volume in the, unit surface area, pointing in the direction I on a surface that has direction alpha in the reference space, not the target space. Now, it turns out that this tensor is not symmetric. I want to contrast that with what would be the Cauchy tensor, the same F, which depends now not on X, but on the position R, because when you talk about the Cauchy tensor, you talk about the force at a particular point in space, not at a particular point in the reference volume. So you would say here, okay, the X has gone to an R, and I want to know now, it's still true that the forces have to be transmitted across the surface, but now it's across the surface of the contorted system. So we're going to call this d sigma Cauchy ij drj. Okay. Now this guy has to be symmetric. Well, first of all, let's make the observation that I can look at the total force on the object. This is equal to the integral. Now I'm talking about the Cauchy case. I'm going to come back and talk about this in a moment. This would be the integral over the volume, actual volume in space, times this d sigma c ij drj. Now at this point, you're free to do all kinds of things like integrating to the volume, etc., integrating to the surface, etc. But I don't want to do that. Sigma is a property of the material. It's something that came from the Ks, etc. And when I'm outside the material in question, the sigma is no longer there because this is the set of stresses that come from the internal volume. So if I have something like this, I'm free to say, okay, I'm going to integrate over all of space, and I allow this guy to keep straight whether or not I have an elastic modulus there or not. So that means that I can immediately take this to some dsj. So this is over the domain D, and this is over some surface of sigma ijs. And I take this to be outside the domain of the sample. So this goes to 0, and we correctly get that the internal force is 0. In other words, the forces interacting between the points is not going to cause the object to move. Now, we also have a constraint on this guy coming from the torque. So we have dLi dt. L is the angular momentum, is equal to the integral over all of R of epsilon ijk rj times fk. And this is, again, d sigma kl c drl. And now I can integrate by parts and write this as integral d3r d by drl epsilon ijk rj sigma kl minus integral d3r epsilon ijk drj drl sigma kl. Now this guy, of course, integrates to the surface, and if the surface is outside, we have the same procedure that happened over there, so I can make that guy go away. Here, however, this guy sets j equal to L, and we have a d3r epsilon ijk sigma kl. And that's an integral over the bulk. But remember, we can't have self-forces giving us a change in the angular momentum, so this guy has to be 0. And an easy way to accomplish that is to insist that this is the Cauchy tensor, to insist that this Cauchy tensor be symmetric under interchange of k and L, because it's multiplying this antisymmetric thing. So this is often, the conclusion is often that sigma k, say kl, has to be equal to sigma CLK. Now it turns out that that's not completely true. As long as you're talking about a sigma k that over the sample is a constant and has no gradients in it, then it's true that this has to be symmetric. And it's also true that whatever your stress tensor is, you can find a symmetric version of it. But just to tell you how things might go, suppose sigma CKL was equal to derivative with respect to P of some other variable SKLP. Then I could have this thing be antisymmetric in K and L, but I have a P here outside so that when I take the derivative, I can do an integral by parts and get rid of it again. So you can have antisymmetric contributions to sigma if it's in the form of gradients. If you prefer to have something that has gradients in it like this, you can always do an operation to make this part be symmetric without changing the force. But for our purposes right now, let's assume that this says that sigma KL is symmetric. Okay? Okay, now we're going to go back and look at this other stress tensor. Yes? Yeah. 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 It does not have, it is not symmetric necessarily. Well, because the, see here, I erased it, but when I look at the torque, there's an R and a d by dr. Here, I would need to do the same thing, because remember, this force is in the target space, and this the torque would be R cross F, not X cross F, right? Okay. So now I want to ask the question about, how much work does the stress do? So let's look at the change in the total free energy. So this is the total elastic free energy as a result of a small change in the displacement U. So that should be equal to the integral d to the dx, and then it should be the force F, trying to make this be a different symbol, Fi of x times delta U ui of x. U is also in the target space. And this is the work done by the internal forces, so I need to put a minus sign there. Right? Okay, now I replace this guy by the d alpha sigma I alpha, and I'm going to put a capital 1 here. It turns out this guy, this is called the first Piola-Kirchhoff. And there's a prize given for anybody who can spell Kirchhoff correctly. Only the Germans would do this. 2 H's in a row, right? The stress tensor. Okay, so I'm replacing the F by this. And now we can do an integration by parts. And we'll do the same thing again, that this breaks up into a surface integral, which then we take the surface outside matter, so we'll throw that away. And then we get here integral d to the dx, sigma I alpha I d alpha du I, with a delta here. Let me make sure the delta goes there to say I'm talking about a small displacement. Okay, now this is equal to delta lambda I alpha. So what that tells us is that the first Piola-Kirchhoff stress tensor, notice it's mixed, and so that gives you a signal that symmetry operations would be strange on that. This is simply equal to the functional derivative of x with respect to f with respect to u alpha of x, which is the derivative of the elastic free energy with let's leave it like this, because we don't want to restrict ourselves to a constant u. Okay. Now, we know what F is and how it depends on the strains. F is a function of, actually, I wrote the wrong thing here. Somebody should have stopped me. Where did I make a mistake? This is wrong. Should be looking at this equation. This is delta lambda I alpha. And I can write this as df d lambda I alpha. Okay, so this squiggly f, I wrote it differently over there. This is the elastic free energy total. Okay? This is the elastic free energy density. Maybe I should put elastic here just to elastic. Roman elastic. But F, remember, is a function of U tilde so this is preserving the rotational invariance. So I can write this as df elastic of U tilde du beta gamma du beta gamma d lambda I alpha. And remember, this is lambda transpose lambda, so that's a derivative we can take. And rather than do it for you, I'll just remind myself which side it goes in on. Where are we here? It turns out that this is equal to Where am I now? I am. I wrote it down here somewhere, didn't I? Oh, yes, it's lambda I beta sigma 2 alpha beta, where sigma 2 and this is the second Piola-Kirchhoff stress tensor. Now, what is this guy really? Notice that once I write, what this tells us is that sigma I alpha is this guy. So I can go back up into this equation and replace the sigma 1 by a sigma 2 times the lambda. So we can say that the delta. So now let me, since I'm more comfortable writing this symbol, that's what this guy should be there, just to do that. So delta F is equal to integral d to the dx times lambda I beta sigma 2 alpha beta delta lambda I alpha. Right. Delta lambda. Right. And lambda I beta lambda delta lambda I alpha is the same thing as delta U alpha beta. Remember, these guys are being contracted with respect to the I there. So what this tells us, and we know this is the case because I've just given you the definition of what sigma 2 is. It's equal to the work done, then there's a minus, no, there's no minus sign here. So this is d to the dx of sigma 2 alpha beta delta U alpha beta. So what we're doing here is that this guy is the derivative with respect to this nonlinear strain variable. And it all fits together in a nice way. Now, if you go to Landau and Lifshitz, he gets to, in his elasticity thing, he gets to this equation with the lambda. And then he says, everybody knows this stress tensor is symmetric, therefore I can replace this lambda by the Uij. And it caused me great consternation. When I finally figured it out, we already had it wrong in my book. So you know that there's, watch out for the elasticity section there. Okay, let's see, what did I want to do now? Oh yeah, so there's one further step, and that's to get the, we do not yet have the Cauchy stress tensor. I've told you what it is, but I don't know what it is in terms of the elastic moduli, etc. So what we're going to do is to take this, we're going to take this equation and convert it. So we have delta F is equal to integral. Now I'm going to convert the x to an r. So this is going to be d to the dr over the determinant of lambda tilde. Then I have see, I wanted to write this as, yeah, well, okay, I'll write it as sigma 2 beta alpha lambda I beta delta lambda I alpha. And now I'm going to convert the derivatives that appear here into derivatives with respect to r instead of with respect to x. So this becomes, I'm going to replace this guy was delta is d by d alpha of ui. This is an x alpha right here. So I want to convert that to a derivative with respect to r. So this becomes a d by d. I want to write, this is a d by dx. I'm going to write d by dx alpha on some function is equal to d by dr I dri dx alpha on f. So I get an extra factor of lambda here. This thing becomes equal to lambda I alpha, not I, let's make this a j, lambda I alpha delta u delta ri dx j. And so now what I've got is a lambda here, and a determinant here, and all of this has to equal the integral e to the dr sigma Cauchy ij times d delta ui dr j. And so sigma Cauchy is 1 over the determinant of lambda, and it is lambda tilde sigma 2 lambda transpose. We can put the alpha beta here. We can put a I alpha here and a beta j there. And you can see now that the sigma ij, the Cauchy one, is symmetric. This guy is symmetric. The lambda transpose is symmetric. So we have the Cauchy thing that we think we should have. Now, fortunately, for physicists at least, all of this nonlinearity stuff is not so important because you look at strains in a piece of aluminum, a big strain is 1%. So you don't really have to worry about the nonlinear terms, and then you can replace u alpha beta by a half grad I uj plus grad j ui, and you really don't have to worry about the distinction between the two that much. But I don't know, for me at least, I felt comfortable when I finally learned this way of doing things, which appears in the engineering literature quite a bit. Okay, how am I doing? I have 10 more minutes or something like that, don't I? When I teach hour-and-a-half classes to undergraduates, you have to have, after 45 minutes, a stretch exercise. And I don't think graduate students are any different. So I thank you for paying attention so long. Okay, so the final step is we want to know what the stress tensors are. So the easy one to do, of course, we'll focus on the second Piola-Kirchhoff stress tensor because that's the one which doesn't involve all the extra lambdas, which we can always put in later if we want to. So sigma 2 alpha beta is d by du alpha beta of the free energy elastic thing like that. And this is then equal to k alpha beta gamma delta u gamma delta. So for the isotropic case, this is equal to lambda delta alpha beta u gamma gamma plus 2 mu u alpha beta, okay? Which also can be written as b delta alpha beta u gamma gamma plus 2 mu u alpha beta minus 1 over d delta alpha beta mu gamma gamma, breaking things up into the volume changing and the shears. I didn't say before that B is equal to lambda plus 2 mu over d, which goes to lambda plus mu in 2 dimensions. So So one can go through the exercise, you know, if you want to know what sigma xx is in general, for example, this would be kxxxx uxx plus kxxyy uyy plus, kxxxy plus kxyxx times uxy, etc. So you can, it's easy enough to calculate those things. Okay, so one final subject about elastic materials is, it's, remember we said that, that lambda, this thing can either be a rotation or a stretch, and it's often important to know how that breaks down. So as long as we have little d equal to big D, lambda is an invertible square matrix, and we have the following theorem, that we can always write lambda I alpha as a rotation matrix times a symmetric, let's just call it symmetric there. That, in fact, this guy is the strain. Maybe I'll leave it like that. But you can always decompose any matrix into a rotation matrix times a symmetric matrix. And it's actually amusing to see how that comes about. I'm going to write lambda tilde as being equal to lambda times lambda transpose lambda to the minus 1/2. Make sure I'm doing this one right. Yes, times lambda transpose lambda to the plus 1/2 power. That's right. Now, so clearly these two guys multiplied together give me 1, and that's a lambda tilde. So I can write, so this guy is symmetric. It's the metric tensor that goes there. This is the square root of the metric tensor. So what we would claim then is that lambda I alpha is equal to a rotation matrix and this lambda, this rotation matrix is lambda tilde, lambda transpose lambda tilde to the 1/2 power. And if this really is a rotation matrix, then O transpose equals O transpose O is equal to delta I J. Yes, right. So it's easy enough to see. Let's take O, which is lambda tilde, lambda transpose lambda tilde to the minus 1/2, and multiply it times the transpose, which is lambda transpose lambda to the minus 1/2 times lambda tilde, because, and there is a transpose here. So you can see that this guy is g to the minus 1, and that we bracket it by this. But did I do this right? It is getting to be towards the end of the day here. I may have. I see a better way of doing it that has less messy algebra. It's already messy, but let's write it this way. This would be lambda g to the minus 1/2 times lambda g to the minus 1/2 transpose. That's equal to That's equal to lambda tilde g to the minus a half, g to the minus a half times lambda here, which is now lambda transpose lambda to the minus a half. Well, it's there twice, so it's lambda transpose lambda to the minus 1. Lambda here, lambda transpose here. Yeah, this one's a transpose, this one's a transpose. And then you take the inverse, which exists, you have lambda inverse, lambda transpose inverse, and you can see they cancel, and that gives me 1. And you can do the opposite order if you wish as well. Lambda transpose inverse, you put the lambda inverse on this side, the lambda transpose, and that works. Okay. Yeah, okay. And you can show that O at small, for small angles, that O is of the form delta ij minus epsilon ijk with a 1/2, I think, omega k, where omega k is a small rotation angle. I leave that as an exercise for you. I think my mouth is giving out. I will open it to questions and not push you any further today. Break time. Yes. So you can, the strain can vary in such a way as to give you torsion. You just have to think about how to do it. I mean, this, if so I have a sample like this, and I twist it like that. That involves, taking this plane and changing it to that direction. So this is locally a kind of shear as I go along, and you can construct it out of a shear. Yeah, I mean, there's some things that some of the torsions are a little confusing to put in. Yeah, I have not spent a lot of time thinking about that, but it is possible. You can do bending and all kinds of things. Yeah. There we go.
Calculation.
Yes.
You said the Cauchy stress tensor could be written as the derivative of a third rank tensor.
Yeah, so there are materials where, and in fact, we run into the trouble a little bit here. But okay, so an example right now, so the a very popular topic right now is odd viscosity. Have you heard about that? So if one way to get the odd viscosity to come out is to write your angular momentum density as a center of your momentum density as a center of mass momentum density plus a term which is a half epsilon ijk times Lk, where Lk is the angular momentum of a rigid spinning object inside. So suppose the thing is made up of that. If you put that in and calculate what the stress tensor associated with G is, it's going to have anisymmetric terms which come from that angular momentum. But there are ways of collecting those things together so that it is symmetric. I mean, you have to do some manipulations. The same thing happens in high energy field theory. You end up with terms that are like, see if I remember how that goes. You have a df, a d energy, d some tensor multiplied times the tensor. That a vector. It's a d energy to a vector. D energy, d e field, for example, and then one of the stress tensor has that thing times e j, and so it's not symmetric, but it's such that you can play a bunch of manipulations with the algebra and convert it to a symmetric thing, and it's because it's the force that's important, and anything that gives you the correct force density is right. Now, of course, if you're going to go ask what happens at boundaries, you have to be a little more careful, but when you have a gradient at the boundary, it also goes away. So most of the time, you're safe looking at a symmetric tensor, but it's in the standard format for the stress tensor of a pneumatic liquid crystal is antisymmetric, and you have to work to convert it to symmetry of a pneumatic.
Surface or whatever you are going to talk about, is this important? I mean, this asymmetry in the stress tensor, when integrated on the surface, it's going to give me something.
So what, you know, the simplest surface calculation assumes that you have a vacuum on the outside, in which case your stress tensor is set equal to 0. And so if it has an antisymmetric part, you don't want to fiddle with it. Now, when you have two things together, I actually have not done the calculation both ways, but if you're careful, you're guaranteed to get the same answer. The gradient, the extra term generally has a gradient in it, so that the force has two gradients. And the question is which gradient goes with the outside and which is on the inside and so forth. It's, yeah. Mm-hmm.
So I had one small question.
Yes.
In all this treatment, I guess you don't need the displacement to be small, right? You just need the strain to be small. So the displacements could be large. Is that right?
Oh, the displacements, of course, the uniform displacement is, yeah.
No, but like if I have beam and it is a huge,
Oh, yeah. So that's one of the reasons you can get away with it. Yes, you take a beam and do that, and almost everybody looks just at the linear tensor. An even more striking one that drives me crazy. You take a piece of metal that's been made in a foundry, and there are grain boundaries all over the place. And people then pop in and say, okay, I'm going to calculate the grain boundary energy and the distortions using the linearized elasticity. Well, wait a minute, I have a grain boundary here, and I bent the thing so that, on this side I have that, and on that side I have that. How can you use a small strain? But the point is that you do have, locally it's a small strain and you get a big twist. But even that, I would claim that is not fully understood by anyone. I've heard ridiculous talks by engineers who nonetheless, know how to make something that doesn't fall apart most of the time. So, yeah.